Welcome back. Chem 110B, Chapter 9. This is a dilution without reaction problem with just water. It's one of those beaker problems. It can be found on page 149 for the explanation and example. And these are exercise 9G problems from number 1, 2, 3, 4, and 5, but only those. The setup's going to be the same for anything from Chapter 9, exercise 9G, but we're going to sort of split up the kind of problems that we do. So the thing to remember is that you have to be careful to make sure that you're organized and you know what it is that you're calculating. There's lots of different calculations you can make, and your job is to know which ones, okay? So here's the problem. What are the ion concentrations in a solution made by mixing 17 milliliters of 2.20 molar K2CO3 solution potassium carbonate with 25 milliliters of water? The wording of the problem allows me to draw the beakers, and I like doing that so that I can have a visual of what exactly it is that we have here. Ion concentrations in a solution made by mixing 17 milliliters of 2.20 molar potassium carbonate is mixed with 25 milliliters of water. Remember, the mixing doesn't get completed until the arrow. That beaker is separate from that one. All this has is water in it. When we pour them together, what are the ion concentrations? Well, what are the things we need to do here? Well, the first thing we know is 17 plus 25. Careful with our sig figs, is total volume at the end is 42 milliliters. We know that for sure. Second, we know that splitting this up into its individual ions, the K plus concentration is something, and the carbonate concentration is something as well. And our job is to try to figure out what that is and what that is. Third, our ultimate goal is to find out what the potassium and carbonate ion concentrations are at the end. Okay. Because there's no reaction here, that means we're going to keep track of the moles of each ion as we go. And we know a couple of things. We want to find out what that is there. We also know, because all we have is water here in this beaker, that there's no potassium ions that come out of that beaker, and there's no carbonate ions that come out of that beaker. Okay? Notice how the moles from each ion track with each beaker. And that was really going to help us stay organized here. So, I'm not sure if this helps you or not, but while we're writing this, it's clear that we're trying to figure out A, B, C, and D. These are the 4 different calculations that we have to complete here in order to finish this problem. First thing we have to do with ions in solution is know what the concentration of the ions are in this solution here. Alright, so the calculation for A should be pretty straightforward. 2.20 moles of the potassium carbonate per 1 liter, and you know that there's 2 moles of potassium ions per 1 mole of the formula unit, K2CO3. 2 of them. 2 of the K pluses. So that's 4.40 molar K plus in the first beaker. I like putting that information carefully in the wording That's what I mean by staying organized and carefully labeling, so I know where I'm calculating what. The carbonate ion concentration is calculated much the same way, but with a different ratio in this case. What is that ratio? How many carbonates are there in one potassium carbonate? That's a 1-to-1 ratio. These are like ears, and the carbonate ion is like the nose. It's a 1-to-1 ratio for potassium carbonate, and a 2-to-1 ratio for potassium ions in carbonate. 1 mole of carbonate ions per every 1 mole of the compound leads me to 2.20 molar carbonate ion in first beaker. Remember, if you're not so good at splitting these up into their ions, seeing that's chapter 3 stuff. Okay, so that's 2.20 molar goes there. But remember, we don't have 1 liter of solution, we have far less in this beaker, and even far less at the end. So we have to calculate the moles. Every time, get ready for this, that you have a concentration of an ion in moles per liter and a volume. You're going to have to figure out the moles. So how do we figure out the moles of potassium ion? Well, that's just concentration times volume. What's the volume? Quick shortcut, 0.017 liters. Guys, get used to that. That's 17 divided by 1,000, or times 1 liter over 1,000 milliliters. 1, 2, 3. That's going to be something that I use a lot because it saves some time. About as much time as knowing what these ratios are and quickly being able to write down these concentrations. You may see me skipping that step as well in the future, but we'll write them all out for now. Okay, so what is 4.40 times 0.017? To 2 sig figs, 4.4 times 0.017 is 0.0748, or 0.075. And guess what? That's not enough. And that's not enough. And that's not enough. That's the full deal. That's exactly what you need to know. That answer gets written right here. That's the number of moles of potassium ion that are found in that beaker. Okay? Let's do D, and I'll write out the whole calculation here. Concentration of the carbonate ions is 2.20 moles of carbonate per 1 liter. We're going to multiply by 17 milliliters, and then 1 liter per every 1,000 milliliters. And again, to 2 sig figs, that's going to give us .0374, or 0.037 moles of carbonate ion first beaker. And that goes where D is telling us that information. So we found the moles of each ion that come from that first beaker. Since we're not adding anything but water from the second beaker, we can add them together and find at the end we have that many moles of the potassium ion, and that many moles of the carbonate ion. But that's not what the question is asking. It's not asking for how many moles, it's asking for the ion concentrations. How do you find ion concentration? Concentration is moles per liter. So how many liters are we dealing with here? Remember, we're at the end. That number of moles is no longer in 17 milliliters, it's in 42, or 0.042 liters. Okay? Writing things along here with the third beaker, the final solution, allows us to be careful about what it is that we need to divide by. And when we do that, and I use the whole value, I don't think it'll change. This is 0.89 molar carbonate ion, 0.075 divided by 0.042, 1.8 molar potassium ion. And before you leave the problem, you'd better think it through and see if it makes any sense. If we start with 2.20 molar and we add a bunch of water, for sure the concentration is going to go down. If the concentration of potassium ion started at 4.4, it's going to go way down. 2.2 going to go way down. Good. Now, if we had added 17 milliliters, it would have been a 50-50 dilution, and the final concentrations would be exactly half. But we added more water than just 17 milliliters, so it should be less than half, slightly. 2.2 would be half, slightly less than half. 1.10 molar, slightly less than half. And remember, this is going to limit the number of sig figs in your answer. Okay, that's it. This is not hard. These calculations are simple. Addition and subtraction is simple. Taking concentration from moles and volume in liters is simple. The key to this is being careful and organized. Give it a try, 9G, 1 through 5. Good luck.